in the previous slides, we showed how to transfer a line to a dot in the radon domain. And now we discuss the radon transform or Topi transform in the context of seismic data analysis. So this is a typical time X domain data set. So for a hyperbolic curve here, reflection, see what looks like in the tau p transform domain. So we transfer line by line. Each line is a constant p, right? And the interception time at x equals 0 is the tau. So that's the tau p here. That's the p. That's the tau. Tau equal to p minus t minus px. That's the tau. Tau is the t minus px. Okay. So when the x equals 0, t equals to t naught. So that's the tau. Let's show you. If we have a horizontal line, which is a p equal to 0, that's the p equal to 0, right? And the tau is here, tau is here, p is 0 over there. So this if you do the summation along this line, you end up energy here. Of course, everywhere 0 only have this dot. You have a dot here, right? And then you have different p. For example, you have p here, and the tau is over there. So p is this one, and the tau is here. You sum up all the energy along the straight line, and put this energy in the tau p position here. And another one, that's the straight line. And that straight line is 1 over v, because that's a direct wave. Straight line is direct wave, right? So the p is deep. Deep is the inverse velocity, so it's 1 over the v. And tau is 0, so tau is 0. And the p here, we know that p is 1 over v. So maximum p in the tau p domain is 1 over v. So this curve, after tau p transform, becomes this curve, right? So now we have a general conclusion. A hyperbolic curve in the tx domain after transform becomes, what's this? Ellipse. Yeah, a quarter of ellipse. You can see that? That's ellipse, right? So the main axis of ellipse is 1 over v. See that one? And the short axis actually is t naught. So that's the curve. If you have another curve, you will have another curve here, another curve here, right? So that's the feature of reflections in the tau p domain. And when you do summation, everywhere is 0, but next to point B, you not only the single point, but the neighboring points will sum together. Actually, this radius called a Finney zone, right? Which is 1 over, which is a quarter of a wavelength, a quarter of a dominant wavelength here. Okay. That was for single hyperbolic curve. We have a multiple curves. Each of those is a ellipse. and they have, in this case, have 4, so you have 4 ellipses, right? That's a tau p transform. That's show together Tx, and that's a tau p. We not only keep a positive p, but we also leave some negative p here in case you have events in that direction, right? Typically, for the complicated subsurface geometry, or sometimes you have aliasing issue. Sorry. So you can see this ellipse here, ellipses here, yeah. And this straight line, that straight line actually is caused by a dot, a single point in your Tx domain. So a line in the Tx domain becomes dot in the tau p domain, and a dot, a single random noise dot in the Tx domain becomes a line in the tau p domain. Okay, so this is basically those are the noise. If we want to get a random noise, you simply cut off this, right, and then do the inverse tau p transform. You can get over the noise. So just a summary. In the Tx domain, a line becomes a point in the tau p domain. A point in the Tx domain becomes a line in the a point in the Tx domain becomes a line in the tau p domain. A hyperbolic curve in the Tx domain becomes an ellipse in the tau p domain. That's the corresponding in the two domains. So how do the inverse tau p actually is exactly another tau p transform, right? Because they have a different curve, different line, so that we do not need to spend more time, just exactly another tau p transform. Just a stacking. Let's show you some examples. That's import 3 gathers here. That's after tau p transform, after just see that where the tau p transform, the fertility of the tau p transform. That's input. You do the tau p transform and the inverse tau p transform, end up this result. So the difference between the two show here. Right. If you have a perfect transform, mathematically, if we're talking about Fourier transform, for example, which means we can 100% recover the original data, original signal. That's called transform, right? So called tau p transform, I just try to emphasize here that tau p mathematically is not a transform, which means when you do the inverse implementation, you cannot 100% recover the original data. Right? This is the example I show here. Input here, you haven't done nothing, just do the tau p transform and the inverse tau p transform. You can see the difference here. Okay, why is that? Anybody know why we didn't do anything? We just do the transform and then come back. We couldn't recover original one, but we have a residual here. Any idea? Okay, let's go back. It's simple as that. If the integration is from negative infinity to positive infinity, we end up perfect transform pair. However, we have only limited offset, x direction only limited in this case, right? So you have the edge effect. So this aperture is one of the very important parameters for the tau p transform, right? So if we go back to the previous definition here, did I put definition? I didn't put the mathematical formula here. So basically we call the transform means we assume, for example, this one, the angle from 0 to pi, which is basically a circle, right? And then another in the opposite way. So this is a complete circle. But in reality, we only have a limited offset, limited aperture, right? So that means at the edge here, when you do the summation, okay, sum of that. But when you do the inverse, you don't know this point should be only belongs to this point or belong to energy also beyond this point. You can see that. So this is the edge effect or the aperture. Aperture means the span range. That's the key point. So ideally, you know how to minimize the edge effect. We learned it before. We do tapering. We gradually we multiply different weights to the traces. Typically towards the edge, you gradually reduce the weight. That's called spatial tapering around the x direction. That can somehow, but the tapering itself already reduce all your data, right? But in terms of transform, forward and inverse transform, we have perfect recovery, but tapering itself already have some effects, okay? So this is the difference between the reality and the theoretical formula. Theoretical formula you should be able to integrate from negative infinity to positive infinity. Even the symmetrical, you at least have from 0 to positive infinity, right? So that's the tau p transform test. You should know this one's nothing to do with the numerical implementation, but because of the data, we only have limited aperture here. Right, that's in the tau p domain representation. P0 here, which is a flat line, P0, and have a positive value P, negative value P, right? And the vertical axis is tau. And the curve here, most likely we saw it before, just like a ellipsis, right? In a form ellipsis. One question: what's this happen? Why we have something here in the negative P? Use your knowledge from previous lessons. That's a wraparound. Remember when we do that Fourier transform, if for single seismic trace if we do not have a sufficient zero padding at end, so the periodical signals actually they will have an overlap, right? So the start point from the second period actually overlap with the end of the first period, right? That's the thing here. That should be somewhere here. Okay. So that actually tells you one more thing, how this tau p transform implement actually is in they use exploit Fourier transform, right? Because FFT, fast Fourier transform, is very fast. So much faster. So that's one. And the problem is the implementation they just didn't have enough padding. Okay, that's the wraparound. So in this diagram, for the p equal to 0, it's flat data. Here, increased dipping angle, gradually increased. And just a steep dip at here, steep negative dip over there. And okay, that's the explanation here. Tau basically is the intersection time. That's the maximum available P, as I said, is 1 over V, 1 over direct wave. In this case, the P value is 667. Well, it's actually inverse of that, which is 1,500 meters per second. We know that it's water, right? Water environment. So that's the water marine seismic acquisition. That's wraparound here. You can see that from your note. Have we plotted? Yes. I think we include the notes here. Now, we're talking about wraparound. The anything issue, we have if we see some coherent events in that way, we call it anything. But we're talking about wraparound. It's not wraparound means if time here, shot here, but this part of energy actually floating back in the time axis, floating back. In the tau p domain, this part is floating to here. That's the tau p transform. That's talking about negative p, right? Negative p, because we said if we have an Edison issue, we have negative p. So that's why we also, when we display tau p, we not only from 0 to positive, but also to display the negative p in case you have an Edison energy. That's the Edison energy in the negative p, right? So that means after the tau p transform, we can simply remove any negative p. That means we remove Edison issue, right? Okay, that's the way to do that. And so this diagram shows you two things. One is Edison energy, and also the wraparound over here. This is one thing here. Because of this Edison issue, the tau is over here. The tau is beyond the maximum tau. So where the tau goes, of course the tau will go to here. That's the logic. Let me repeat. If I have a negative energy, the tau is here larger than the maximum T, right? And because of periodical assumption, so this larger tau will be float back to the beginning. So that's the wraparound. The same thing occurred in the FK domain. So tau p is another. Actually, tau p transform is between the TX domain and the FK domain, just in the middle. Right? We only do the one transform, Fourier transform. Now let's based on the behavior in the tau p domain, we can select the different mode of signals, different mode of coherent noise, and do the filtering. So FK filtering, this FK filtering, tau p is similar to FK filtering, but tau p has a trouble, which is not so-called AVO friendly. AVO means amplitude variation versus offset. You can see that because we do summation along the offset, right? We mixture all the energy at different offset. And after the inverse topic transform, we spread single energy into the line. So that we sum all variation along the line becomes single point, but the inverse Fourier transform, inverse topic transform, we spread a single point into a line. That means we somehow distort the amplitude variation versus with offset, right? So that's not AVO friendly. So if your main purposes is for AVO inversion, AVO is a very important feature, very important information for reservoir detection, even for the different fluid detection, separation, like between the gas and the oil, or between the water and the oil. If we want to keep those, you should be careful. Topic transform might damage this information, right? So, okay, because it's global method, so the summation over a line will destroy the variation of amplitude. That's the thing. Tau P allows localized deep field because you know that unit P, right? So we said if we try to get rid of a negative P, which means we get rid of the Edison signal, noise, right? To improve the signal to noise ratio. It is controlled by time because the P is constant from all different times, right? So you better, if for different time, use a different P. So that should be variable with time. The application should be variable with time. As we showed one example, we have the wide ellipse for shallow hyperbolic curve, but for the deeper one, the main axis of ellipse is gradually shorter because the velocity gradually higher and higher, right? So this application should be depends on the travel time or interception time. And this one can be implemented by so-called least square transform. Okay, we are talking about least square transform in the next session when we're talking about the parabolic ladon transform, but the same way to do the same principle. And here I just tell you why we do the least square transform. We already saw that in the previous slides when we do that ladon Tau P transform test. After forward and the inverse transform, we do not 100% recover the original seismic data sets, right? We have a residual, have difference. And the difference actually caused by the edge effect, Because in the ideal situation, the summation or integral should start from negative infinity to positive infinity, but we only have a limited aperture, right? Okay, so what do? We try to use the least square, which means within the limited aperture, we try to have a maximum, we try to have minimal difference between those input and output. That's called the least square, right? The concept that we mentioned when we're talking about deconvolution, right? So if we go back to this diagram, so this square really means we in between Tau P transform forward inverse, right? We try to see this one and this one, the difference is here. We try to minimize the square of each individual point. That's called least square. Minimize the square. Least means the smallest, right? So that's the concept form. For application, right on not right on. Tau P transform is a time variant deep field. Time variant deep field. In the FK transform, we do the slope. We call it fan filter, right? Fan filter, we only explore the K over F ratio, which is different dip angle. But here, because we have a dip, depends on time, so tau and P. So that means we can apply dip field based on the different tau. So it's time-dependent dip field. That's, you see the advantage compared to FK. FK, you only have a constant dip because you already do the transform from T to F. But here, T actually is equivalently equal to the tau, right? We call the tau means the interception time, but actually it's time T. So we keep the T. So that means we can use time variant dip field, okay? And the main purpose here I will show you is that multiple attenuation, because the multiple has a different velocity from primaries. So that means 1 over the velocity is P. So that multiple have a different dip from the primary, right? So that we can use a dip filter, time variant dip filter to do the multiple attenuation. That's the one thing. Second thing I will introduce here, use deconvolution for deconvolution. When we're talking about the particular decon in previous sessions, the one assumption there is the multiples is predictable. So basically, second order multiple, third order multiple have a same time delay as the first order multiple, same time delay as the water bottom refraction. That's predictable. But this assumption only varied when offset is very small. Basically, regression only varied for 0 offset, right? But when the offset increases, this periodical assumption will not satisfied, will not be satisfied. So after the tau P transform, you can prove that after the tau P transform, for all different P, for constant P, that's time period is constant. The time period is constant. So in the P domain, the multiples have a constant time delay. So that's predictable. How to understand? It's easy to understand that way. As I said, P is a rare parameter. It's sin theta over V. I did mention in the previous session, P is constant along the travel path, rare path. Doesn't matter how complicated of the subsurface media, how complicated the rare path is, P is always constant along the single rare path. So multiple and the primary, or high order multiples, they're actually on the same rare path, right? So that means they have constant P. So following the single constant P, the multiples are predictable. That's the way to understand it, right? Easy to understand. So that means we can use tau P as a tau P domain. We transform TX domain data to the tau P domain, and then do trace by trace deconvolution the tau P domain. And then you do the inverse tau P back to time. Okay, I'll show you this. Also, you can do this called interpolation, but in this lecture, we do not talking about much about, but we are talking about these two applications. But there's an input shot. I have 3 shots here. If we try to do the tau P transform, this actually have a positive P in this way, right? P and 2, 0, and the negative P here. So this curve you can see from here to here, right? Now, for anything, we know that this the maximum P value is here, 1 over the V. Anything beyond that, that's noise, right? So we can remove this noise, and then remove this noise by mute out this part, mute out this part. You only keep the perfect ellipse here. Get rid of this left, get rid of the right parts, and then do the inverse Taopi transform, see what it looks like. Okay, this is the part, the Taopi noise, the noise in the Taopi domain you removed, and after transform you can see much cleaner. The first arrival is gone, right? First arrival is gone. Let me go back to that's first arrival, and also this have a dispersion effect here. Up. You mute in the Taopi domain, and I see much clear reflections, so enhance the signal to noise ratio. And that is the difference between the original 3D shots and the Taopi filtered shot, right? You able to remove most of this. But also you also remove something here in this way. But it's just Alice in the issue, actually. It's Alice in the data. It's not necessarily in the original data. That was for the multiple, for the noise attenuation. Very simple, straightforward. But mainly in the Taopi domain, we try to do something called predictive deconvolution. We learned this. Let's review what we learned about deconvolution. So far, we learned 2 types of deconvolution. One's gap decon. Gap decon means predictive deconvolution. Another one called a spark decon. The purpose of spark decon is try to narrow the source signature, right? Try to narrow source signature. And the predictive decon try to remove the multiples, right? And if you check the effectiveness of this deconvolution, you will do the autocorrelation. Just see whether your purposes actually achieved or not. Okay. So for spark decon, we try to attempt to correct for the source. We try to correct for source signature. Try to, for example, get rid of source ghost in the marine environment, for example. And then also sometimes can get rid of some very short period of multiple, for example, bubbles next to the shots, right? Multiple bubbles. And in the spark decon, we assume the reflectivity is wide. So that means you should have a long enough seismic trace. That means you have multiple layers, multiple reflectivities. So the reflectivities should be in wide. That means you have enough reflectivities. But also you assume the signature is minimum phased. For the air gun or for dynamite sources, that you can assume the minimum phase. But for the warp seismic is 0 phase, right? Remember, you convert your sweep signal to your seismic record. Actually, the source signature is 0 phase. Autocorrelation is sweep autocorrelation to itself. Autocorrelation is always 0 phase. So spark decon cannot apply directly to the seismic data generated by the websites. That's the one thing, right? So just as I said from the very beginning of the lecture, one of the objectives is to try to understand the the limitations, right, of each individual processing steps. So in this case, there are two assumptions. One is a wide reflectivity, another one is a minimal phase. So when these two assumptions are satisfied, you can use spark decount to your data. Step decount or predictive decount, you try to remove short period multiples, and also long period multiples you can remove, but the period must bigger than the gap, right? Because within the gap you try to keep the signal untouched, okay? And also assume the wide reflectivities, so you should have enough recorder length, it should be long enough. One assumption here is multiples are periodic. You must, in your autocorrelation of seismic trace, you can see the multiples, at least 2 or 3 repeated period. Otherwise, you cannot do that. The spark-decount and predictive decount, we learned before predictive decount is to try to remove the multiples, right? But do not reshape your signature. But a spark decount should do the different way. Spark decount try to process the signature. I mean the wavelet. Wavelet includes the source signature, include instrument response, all the effects, right? Including the subsurface effect. That is called a spark decount. Try to basically narrow your source signature, narrow your wavelets. And it can include a short period multiple, but it's not the key point here, right? And those two, although we call the two different deconvolution, but in the software, they actually in mass spectrum, they're actually single software. They are single software, single same mass spec formula. Only difference is the gap. For the gap, for the spark decount, the gap is one sample, only one sample. But for the predictive decount, that's a gap, it's a period you try to keep untouched. So one sample means for the first sample, you don't untouch, right? And now, because we know how to do the tau p transform, spark decount and the predictive decount can implement better in the tau p transform. Let's do that way. Let's do this in the next slides here. Oh no, okay. Let's see the diagram here about autocorrelation in the deconvolution. So this is the autocorrelation of seismic trace. If we have a time zero leg zero, you have events here, and they have a negative polarity, positive polarity, negative polarity, so it's periodical. So that's the multiple, right? For the spark decount, you just use a single spark, just keep it at 1 point untouched. But the operation field is, if there's short period, you just gather of energy here, right? So after the autocorrelation, you have a very narrowed, basically field spark. It's not a necessarily single point field spark. If you have a long period, you can gather also the multiple here. You can see that, right? So you can have both multiple attenuation and the designature at the same time, but we recommend you do it separately, just see the different effects to try to. For the predictive decount, you have a so-called the gap here. Gap means that this from here to here, the signature will be untouched in the predictive decount. And based on this one, predictable signals this and this. So if you use a predictive decount, you can get rid of this one. After the predictive decount, you do the autocorrelation of seismic trace. you end up this, right? So this one disappear, that one disappear. The first order multiple, second order multiple all disappear, right? You say you worry about it, the reflectivities, right? Some reflection. Because we assume the reflectivity is wide. Wide means the autocorrelation is 0. So this one does not affect your reflectivity, does not affect the promise. Because we assume the reflectivity, that's why we assume reflectivity is wide. The issues with the deconvolution, one issue is the multiples are not periodic before stack. In the previous, in the CMP gather, that's not periodic. After stack, because all the traces, non-zero offset traces, actually after NMO, we transfer the non-zero offset trace become zero offset. That's the purpose of NMO, right? So we can assume the result will be periodic if your after NMO. Before NMO, before NMO correction, your travel time changes with offset. Travel time changes with offset, so this is not periodic. That's the issue. Tau P deconvolution. So multiples after the Tau P transform, multiples becomes periodic. That's before stack, but there's another assumption here. It's called 1D Earth, right? For 1D Earth means every layer, water bottom, and all the subsurface reflection is flat. So you only have variations in the vertical axis. That's called a 1D Earth. Horizontally, you can assume the constant. So in the 1D Earth, the multiples will be periodic after Tau P transform. That means we can have a better implementation of a particular decal. Right? Okay. One thing here, maybe you need a spherical divergence correction. We said particular at here, we're only talking about time period, right? Time period. But different offset means your travel distance different. In fact, that means your energy will be different. Spherical divergence, right, for single point, and then the wavefront gradually becomes larger. The radius of the wavefront becomes gradually larger, larger. The amplitude becomes gradually smaller, 1 over the r. So the spherical divergence factor should be considered, or you need to compensate, right? Typically, for the Tau P transform, as we said, we do one CMP gathered by one CMP, which is 2D line, Tau P and the Tx, so 2D, but in reality, your source is a point source. You have 3D effect, so you do need to do some correction. That's a technical issue. Can easily do the compensation. Just show you examples here. That's the input data after the Tau P transform. So the Tau P transform, you have the ellipse here, right? You can see here is a tau equals 0. No, sorry, tau equals 0 is here. Tau equals 0 here, right? So after that's the two short gathers, two CMP gathers after Tau P transform, and then you try to gather for this part. That's mute, right? You can mute out this and also mute out this. What's this? They have constant P at different tau, right? Because that's P is here, horizontal is a constant P, and the vertical tau, different tau. Constant P, different tau, what is this? Most likely like a direct wave, right? Just, or something similar to direct wave. They have a different P, same P, but at a different in the second time, okay? So you need to mute out this, and then in the tau P domain, you do the particular decom. Okay, let's see the mute. That's the difference now. We get rid of something, the straight line here, but this is the edge effect. Okay, that's not what we really want. That's the edge effect we said it before. But those things actually were muted, which is direct waves. Okay. Then in the tau P domain, just same as in the TX domain, when we do deconvolution, first thing we do the autocorrelation of individual. Each trace you do autocorrelation. You can see that we also have a slight the lag delay, time lag here. So you have a zero lag, and then the multiples. Clearly, you can see that, right? And they use exactly time domain deconvolution. You do the deconvolution because the vertical axis is time, right? To decom. After that, you can see you only keep the first zero lag here, and all the multiples disappear. Okay, that's input output. Between these two, the difference you show here, that's the multiples removed, right? That's in the tau P domain. So you apply the deconvolution in the tau P domain. The module already there, tau P transform deconvolution already there, tau P transformer. So you can now we combine the two steps together, set up like a processing flow chart. You do that. Okay. Now let's see after the tau P transform, after the tau P deconvolution, and then you do the inverse tau P transform, see what it looks like. That was the input trace. We target at multiples, okay? That's input trace. And as I said, that's the multiples. Multiples is a wave travel, in this case, bouncing within the water layer, up down, bouncing in the water layer, because the water layer is a homogeneous media. So you do not have much energy loss, right? So the energy always strong. Because all the multiples have strong energy, okay? And all the primaries, because it's in the deeper part, so all the primaries are relatively weak. So you need to get rid of the strong multiples and then reveal the weak reflections, okay? And this is the two difference between the two. You end up here. That's difference. You can see you have a strong multiples here and a strong multiples here, right? And then now you can, well, most likely the other subsurface reflection. Maybe you have internal multiples, but you get rid of most of water layer multiples. Okay, that's the difference. If we compare this tau P domain deconvolution to the TX domain deconvolution, we call it conventional deconvolution. You can see the difference here. Let's see this one. We do get rid of multiples here, but this part in the far offset is not as good as the tau P domain. You can see that because in the TX domain for non-zero offset, the multiples are not rigorous predictable, but in the tau P domain, that's much better. You have much better predictability, so you can have a better result. For example, here, if you do see here, you do see some multiple, but it's not as strong as that one. So this actually give you an example. The tau p domain deconvolution is much better than the TX domain deconvolution for multiple attenuation purposes. Okay. As we said, the tau p domain deconvolution is effective due to the 1D Earth assumption, right? You assume the subsurface structure are horizontally flat. It's a 1D model. But if water bottom looks like this, has a dip, right? And this multiple, this pigleg and this pigleg, they have a different time interval, different period. So that tau p deconvolution will not work for this case. Okay, so basically this model isolate, but this model is not for the 1D model. So tau p decon only applicable in the 1D model. Conventional tau p deconvolution does not address the steeping event, and in the in the next stage, parabolic Ladon transform will deal with this.